then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Okay, Riemann sums practice problems part 2. In this particular video, we're going to look at 4 problems. 3 of them are going to deal with finding Riemann sums from tables. And the last one will deal with finding Riemann sums from a function. Part 1 dealt mainly with function, but part 1 we only looked at finding left and right Riemann sums. In today's video, we'll find a midpoint Riemann sum. That'll be the last 2 problems. So we'll do one with a table and one with a function. Again, on these practice problem videos, we're just getting straight to the problem and just kind of going through it without a great deal of detail, or I should rather say without a great deal of discussion on why we're doing certain things. And those questions about why we're doing certain things, again, you should refer back to the video on the conceptual foundations of Riemann sums. So in that video, we took a lot of time to go over the conceptual foundations to understand why we do what we do. And these practice problem videos, we're just practicing problems. But I will go over a little bit. So we're finding Riemann sums from tables, and I will just go over a little bit. It's pretty much the same thing as doing from a function, but I will kind of illustrate on this first example how it correlates to what we do for a function, just so there's a firm understanding. So let me read the problem and then go through it. So it says, Kenya rode her bicycle on a straight trail. She recorded her velocity v of t in miles per hour for selected values of t over the interval from 0 to 16 hours, as shown in the table below. Using a right Riemann sum with 3 intervals indicated by the table, what is the approximation of the integral of 0 to 16 of v of t dt? So we're finding a right Riemann sum. So let's think about the things when we were finding Riemann sums from a function. We first found delta x, which was the width of each particular rectangle, and then that was a common width. So we kind of factored that out and multiplied it by the function evaluated at all values of the independent variable except for the first one. If you remember, when we did a right Riemann sum, we used every number but the first number, and when we did a left Riemann sum, we used every number except for the last number. But from this table, this is pretty much the same thing, except of course it's expressed as a table. And here, one key difference is our delta x, or the width of each rectangle, is not going to be the same. So I just want to look at a graph of a function real quick. And this actually was, I believe, a graph we looked at when we were doing our conceptual foundations. But just what I want to point out, when we find Riemann sums, we have these rectangles. And again, for the way we did the functions, the widths were equally spaced. But anyway, you have the width of each rectangle times the length. This problem right here was a right Riemann sum. You can see right here it's a right Riemann sum. So we're hitting a function on the number of the subinterval that's on the right. We're going to do the same thing here with the table. The only thing with the table is that the width of each rectangle is not going to be the same. So like here, the width were 1. Here it's going to be different for the table. But you know, the width of each subinterval, or the width of each rectangle, is just the difference of the x values, or the independent values in that subinterval. So for instance, 0 to 1, 1 minus 0 will give me this length. Let's say this wasn't 1 to 2 and this went from 1 to 7. And so then the width of this subinterval would be 6. And so to get our widths, they're going to be different. We're just going to subtract our independent variables, which on this graph was x. I believe in the table it's t, but it could be whatever the independent variable is. And our height, again, we're still going to be evaluating the function, since we're doing a right Riemann sum with the value of the function with the number in the subinterval to the right. So let's go back and look at the problem. So if we look at a problem, you know, for instance, t is my independent variable. So my first subinterval goes from 0 to 6. Okay, well, the width of that rectangle is 6. It's just the difference of these two numbers. And I'm going to evaluate the function at the number to the right. So I'm going to find v of 6, which of course is 5. and then I'm going to continue the process. So I'm going to go ahead and work it out on paper. All right, so this one, I believe we're approximating a definite integral. So it looks like it's going from 0 to 16, and the function is v of t. All right, so again, the width of the rectangle, the first subinterval was 6, and the height is 5. The width of the second rectangle, just 12 minus 6, also happens to be 6, and the height is 7. And then the last one, the width of the rectangle is 4, and the height is 8. So just going back on the heights for each subinterval, I'm evaluating the function at the independent variable to the right. So v of 6 is 5, v of 12 is 7, v of 16 is 8. And so notice I use 5, 7, and 8, which are the values of the functions for all the numbers 5, 7, and 8, except for the first number, which is what we do for a right Riemann sum. If it was a left Riemann sum, instead of 5, 7, and 8, these numbers would have been 9, 5, and 7. The width of each rectangle would have been the same, however. All right, so let's go ahead and do the arithmetic and get this answer. So this is 30, this is 42, this is 32. So that's 74 and 30, that's 104. All right, so we explained a little bit on this first one because this is the first table one we went over, and then the subsequent ones we're going to go through a little quicker, a little more quickly. All right, so here's the second example we're going to look at. It's pretty much the same problem, so I'm not going to read it. I just changed the name from Kenyon to Kwame, but it's the same biking problem, and we're approximating this definite integral. It's just this case we're doing a left Riemann sum instead of a right Riemann sum. So let's go ahead and work it out. All right, so this is another definite integral approximation. So we're going from 0 to 13. It looks like a v of t dt, and this will be approximately. So again, I'm going to get the width of the first subinterval, subtracting the independent variables. So 6 again here. And now I'm doing a left Riemann sum, so I'm going to use 8. And then the next subinterval is 5, and then I'm going to use 4. And then the next subinterval was 2, and then I'm going to use 6. So notice the width of each subinterval, 6, 5, and 2, they're just the difference of the t values or the independent variable in each subinterval. And then the heights that I use, 8, 4, and 6, is every number except for the last number, as we do for left Riemann sum. So let's look at what we have here. We have 48 and 20. What's this, a 6? I can't read my own handwriting. Yeah, that's 6, 12. So that's 12 and 48. That's 60 plus 20. That's 80. Okay, let's look at another example. So this next example, this is a midpoint Riemann sum. I'm not going to read the whole problem. And, in most cases, it's important to read the problem, but the information there is not going to change much. It's not going to be revolutionary. It's not going to be paradigm changing. So I'm just going to get to the root of the issue, which is we're going to approximate the integral from 0 to 30 of v of t, and this table represents v of t, using a midpoint Riemann sum with 3 subintervals of equal length. 3 subintervals of equal length. It says here, it's a calculator problem. These numbers actually work out quite nicely, so you really don't need a calculator for this one. But some of them, the way the numbers came out, were somewhat troublesome, so that's why I put that on there. But this particular one, we're not going to really need a calculator to do the arithmetic. All right, so let's talk a little bit about a midpoint. So this is our first midpoint. And the deal with the midpoint Riemann sum, and I believe we illustrated a simulation of this when we did our conceptual foundations, is basically it's going to hit the function at the midpoint of the subinterval versus the right or the left point is going to hit at the midpoint. And the benefit of that is that, if a function is straight increasing or straight decreasing, it's going to have some that goes over and some that goes under. So it kind of balances out. It's a really efficient way of doing a Riemann sum for very many functions. All right, so we're going to find the midpoint. So the deal is, so let's look at how to attack this. Let's say let's say I think my first subinterval was 0 to 5. Okay, cool. Well, the midpoint of 0 to 5 is 2.5. However, I don't know what b of 2.5 is because it's not in the table. And the only thing I know about this particular function are the selected values in the table. So I can't take the midpoint of these 2 points. So when given a table, you're going to have to use 3 points to get the midpoint. So I'm going to go from 0 to 10, because if I go from 0 to 10, I have a midpoint there to 5. And then next I can go from 10 to 20, the midpoint is 15. And then 20 to 30, the midpoint, of course, is 25. So on a midpoint Riemann sum, we have to find a number in the middle. So when using a table, you're going to have to at least use 3 numbers to have a number that's in the middle. All right, so let's go ahead and work this one out. All right, so again, and each subinterval has length 10. And so what am I doing? I'm doing an definite integral approximation. The function is b of t dt. So since each width is 10, I can just do 10 times, because each one's going to have a width of 10. So again, for my first subinterval, I use the midpoint, and so I'm going to have 18. For my second subinterval, 10 to 20, I use the midpoint, and so that's going to be 21. And then for my last subinterval, that's 20 to 30, I use the midpoint, so my value is going to be 23. And we'll just do the arithmetic from there. So let's see, this is 39 and 23, that's 62. And 10 times 62 is 620. All right. So since in our part 1 video, we didn't do a midpoint Riemann sum, for my last example, I'm going to do a midpoint Riemann sum with a function. All right, so here's the last example we'll look at. So it says, find the approximate area between the curve f of x and the x-axis on the interval 0 to 6 using 3 rectangles. Use the midpoint of each rectangle to determine the height. So let's go ahead and work this one out. And before I work it out, let me just point out a couple of things. So this is the interval here. So a is 0, b is 6. We're using 3 rectangles, so n is 3. So those are important things to know. And when we work out the Riemann sum from a function. All right, so I have the essential information written here. So anytime we do a function, even if it's a midpoint Riemann sum, we're still going to find delta x first. So delta x, if you recall, is b minus a over n. So in this example, that would be 6 minus 0 over 3, which is 6 over 3, or 2. So we still find delta x first. And then we also write the numbers of our subintervals first, just like we did when we were doing left and right Riemann sums from a function. So we start with a, and we keep adding delta x until we get to b. So 0, 2, 4, 6. All right. Now, what's different, if I was doing a left Riemann sum, I would evaluate the function f of x at 0, 2, and 4, every number but the last number. If I was doing a right Riemann sum, I would evaluate the function f of x at 2, 4, and 6, every number but the first number. And of course, add those up in both cases and multiply them by delta x. Well, when doing a midpoint Riemann sum, I'm going to evaluate the function at the midpoint of each subinterval. So the midpoint of 0 and 2 is 1, the midpoint of 2 and 4 is 3, and the midpoint of 4 and 6 is 5. Now it's still going to be multiplied by delta x, but the function is going to be evaluated at 1, 3, and 5. So our area is going to be approximately 2. That's delta x times f of 1 plus f of 3 plus f of 5. All right, so let's figure out what these various values are for f of x quickly. So let me bring f of x back here so I can see it. And let me find first f of 1. That's just 1 plus 3 plus 4. That's 8. Let's next find f of 3. F of 3 would be 3 squared 9 plus 3 times 3, 9 plus 4. So that's 22. And then let's find f of 5. F of 5 would be 5 squared 25 plus 5 times 3, 15 plus 4. So that's 44. So 8, 22, 44 are the respective values for f of 1, f of 3, and f of 5. So let's plug those in and do the arithmetic. All right, so let's see. F of 1 was 8, f of 3, 22, and f of 5, 44. So this is 30 and 44, that's 74. So it's 2 times 74, which of course is 148. All right, so that concludes our part 2 video for Riemann sums. I hope you find this beneficial, and we'll see you next time.
Specialize in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.